Welcome to Hartman Math. This is lesson 8.1, Matrices and Systems of Equations. As we begin chapter 8, which is about matrices, and matrices are just a way of organizing data. So we can recognize the matrix. It's got these brackets on the outside. It's going to have a lot of numbers, possibly variables on the inside. So this would be called an M by N matrix, where we have M number of rows and N number of columns. So we list the rows first and the columns second. And each number in here is called an entry. So we could have like A23, which means row 2, column 3, whatever number is there, that's our entry that we're talking about. And the size of the matrix is called the order or the dimension. And it's that M by N. So we might have a 2 by 7 matrix. It has 2 rows and 7 columns. And that's called the order or the dimension. So example number 1, let's take a look at a matrix and determine what is the order of that matrix. Think about it for a moment. There's 3 rows, 2 columns, so it's a 3 by 2 matrix. What about part B? What is that one? It's a 1 by 5, 1 row and 5 columns. So example number 2, we can take a system of equations like we were working on in chapter 7, and we can write it in matrix form. And in this case, because it has the equals, we're going to write it as an augmented matrix. So we use the brackets, and then we use all the coefficients here. 1, negative 5, 2, 4, 5, negative 3, 0, 2, negative 3. And then the equal sign is going to be represented by a dotted vertical line separating that. And on the right side, we've got 4, 0, negative 1. There's our dotted brackets to say it's a matrix, and this is known as an augmented matrix. So the same row operations that we were talking about in lesson 7.3, where we discussed Gaussian elimination, those same row operations apply to matrices as well. We can switch any 2 rows. We can multiply a row by a non-zero constant, and we can add a multiple of 1 row to another row. So the same exact row operations from 7.3. So definition of row echelon form for a matrix, and then we'll talk a little bit about reduced row echelon form. Here are the requirements. If there are any rows that are all zeros all the way across, they have to occur at the bottom. So we can't have any rows of non-zero entries below a row that has all zeros. Number 2, for each row that does not have all zeros, the first entry that isn't a 0 needs to be a 1. And that 1 is called a leading one. And then number 3, for any 2 consecutive successive rows, the leading one and the one higher needs to be farther to the left than the one below it, than the leading one from the one that's below it. So that defines row echelon form. One extra requirement for reduced row echelon form is that whenever any column that has a leading one in it, not just any one, but a leading one, all the other entries in that column need to be zeros. That would be reduced row echelon. So let's take a look at some matrices and determine if they are this and if they are this. So determine whether it's row echelon or reduced row echelon. Pause here, think about it for a moment until you got your conclusion. Is this row echelon? If it is, then we can kind of continue on. It is not row echelon. We have an all-zero row that does not occur at the bottom. Basically, since this is not an all-zero row, it would need to be above it. All right, what about part B? Again, pause until you're ready to come up with your answer. Also no. So what's the issue here? It's the 3. The first non-zero entry in that row cannot be a 3. It has to be a 1. It has to be a leading one. So that one ruins it. All right. Part C. What about this one? That one's a yes. The all zero row occurs at the bottom. First row has a leading one. The row below it has the first non-zero entry is a 1, so that's a leading one. This one doesn't have any, so we're okay there. So one last requirement is that the leading one in row 2 has to be farther to the right than the one above it. It is, so we're good. Now we need to decide, is it reduced row echelon? What do you think about that one? Again, pause here. So let's see. This row has a leading one. Are all the other entries in that column zeros? Yes. This is a leading one. Are all the other entries in that column zeros? Yes. And those are the only leading ones, so it does qualify. It is also reduced row echelon. All right, and one last one to look at. What do you think about D? That one's a no. And it's right here. This leading one has to be farther to the left than the leading one in the one below it. All right, so now we're going to look at Gauss-Jordan elimination for a system of equations. And we're going to do it because we're now in chapter 8. We're going to do everything with matrices. So even if it said do Gaussian elimination, we can still do that with matrices. And if we're doing anything in chapter 8, it has to be entirely matrices. So we're not going to go back to the approach from 7. Although the steps are extremely similar, we just handled everything with matrices. So step number 1 is going to be to rewrite the system as an augmented matrix. Careful on this one down here. It's missing a y. So our augmented matrix looks like this. Now we're going to proceed. Now the only difference between Gaussian elimination, where we would want to essentially achieve row echelon form, which would be 1s in the diagonal and 0s below, that's Gaussian elimination. Gauss-Jordan wants us to get to reduced row echelon, so it basically wants 1s here and zeros everywhere else. That's going to be our goal here. All right, let's start writing this down maybe on some binder paper. If we remember back to our Gaussian elimination, we wanted the first equation to start with x. Therefore, we want the first row to start with a 1, representing 1x. It does, so we're good there. We would then like to eliminate turn into zeros the rest of that column. So we will keep row 1 as is, 1, 2, 1, and 1. So we're going to multiply the 1 by -2 and add. So -2 times row 1 plus row 2. When we do that, we're going to get 0. -4 plus 3 is -1. -2 plus -2 is -4. -2 plus 10 is 8. Let's do the same here. We can just take our row 1 and add to row 3. So row 1 plus row 3, we would get 0, 2, -3, and 6. Now we're going to move on to column number 2, where the middle one needs to be a 1. It's very close, a -1. So I think I'm going to leave it as is for now, and I could probably change it a little bit later let's use the -1 to eliminate the other entries in that column, turn them into zeros. So for now, let's keep row 2 as is. And to eliminate this, let's multiply by 2 and add. So we are multiplying row 2 by 2 and adding to row 1. We would get 1, 0. -8 plus 1 is -7. 16 plus 1 is 17. On to the bottom one, I think we got to do the same thing. So we're going to now multiply 2 by row 2 and add to row 3. 0, 0. -8 plus -3 is -11. 16 plus 6 is 22. Now we want this one to be a 1. Probably should handle that right now, as it's not very close to that. So to fix that, let's multiply row 3 by a non-zero constant. This is row operation number 2. Multiply it by -1 11th. And we would get -2 here. Since we're doing that now, let's do it also and fix this one. Let's multiply our -1 by -1. So negative row 2, 0, 1, 4, -8. And we'll just keep the top one the same. So now we just need to, since we're doing Gauss-Jordan, we need to have these be zeros as well. If we were just doing Gaussian elimination, we would not have needed to have this be a 0. We would just need zeros down here, because then we could do the back substitution. We are doing Gauss-Jordan, so we need to eliminate these. We're going to do it by using row 3. And we're going to multiply the 1 by 7 and add it up top. So 7 times row 3 plus row 1. We would get 1, 0, 0. And then -14 plus 17 is 3. And then to fix this one, we're going to multiply by -4 times row 3 plus row 2. 0, 1, 0. And we would get positive 8 plus -8 is 0. So the nice thing about Gauss-Jordan is we've got our solutions. 1x equals 3, 1y equals 0, 1z is equal to -2, 3, 0, -2. Let's take a look at example number 9. Again, we've got a system of equations, and as the title suggests, maybe this is going to lead to infinitely many solutions. But let's first rewrite our system of equations as an augmented matrix. Notice that the first equation is missing an x, so we've got a 0 there. There's our augmented matrix. Let's go back to our binder paper and work that out. We want our first entry, upper left, to be a 1. It is not. But there is a 1 in that column. So maybe we can switch some rows, move the third row up to the top. And put the top row down to the bottom. Switched row 1 and row 3. Keep row 2 the same. So now we've got our 1. We need to turn the 3 below it into a 0. So we'll multiply our top row by -3 added to row 2, which means row 1 is good as is. So multiply by -3 and add 0, multiply by -3 and add 2, multiply by -3 and add -3 and 3. 0, -4, 6, -6. All right, on to our next one, where we would like this to be a 1. We could multiply that in row by a half, but it would generate some fractions. And remember, the other thing we're looking to do is to eliminate or turn into zeros the rest of the entries in that column. Keep row 2 as is. So we could just add these together. So we are adding row 2 to row 1. And we would get 1, 0, 1, 3. And now for this one here, we're going to need to multiply our 2 by 2 and add to the -4. So 2 times row 2 plus row 3, we get 0, 0, 0, 0. Okay, we got all zeros at the bottom. And so essentially we lost an equation. Now, if it was 0 equals 5, that would be a no solution case. This is continue on, this is actually true, so we can continue on. But we now only have 3 variables but 2 equations. So we know that that's going to be an infinitely many solutions case. Now if we want to continue on with either Gaussian elimination or Gauss-Jordan, we are going to need to fix this. So let's do it now. Multiply it by a half. And we've got our matrix into reduced row echelon form. So in terms of our system, let's let Z be defined as A. So our second row generates the equation y minus 3 halves z is equal to 3 halves. That leads us to y is equal to 3 halves z plus 3 halves. And then the top row is x plus z is equal to 3. So x is equal to 3 minus z. So our ordered triple is now, x is now 3 minus, replace z with a. Y is 3 halves a plus 3 halves. And z is a. Though that is the pattern for the infinitely many solutions. That's it for today. I'll see you next time.